Good morning, team. Chemistry Coach coming at you again with some more lab lecture videos for our lab journey. All right, we're going to look at how to make measurements today. So hopefully you've seen the video on determining the absolute uncertainty of a measuring device, i.e. how many decimal places you can read it to. But I want to go into how to actually do that to avoid or minimize, ideally avoid any kind of error on our part. Minimize it. Worst case, minimize it. Best case, eliminate it. But there's a couple kinds of error. There's human-caused error, systematic error, because we boofed it. And then there's random error. Nothing we can do about that. Well, I guess there is. If there's random error, we could do lots of measurements of the same thing and average those, right? So it's kind of like, flipping a coin. If you flip it once, it could be heads or tails. You flip it 2 times, it could be 2 tails, 2 heads, or heads and tails. And the more you do it, the more likely you're going to have even amounts of both, right? So when you do a measurement, it's possibly slightly high, slightly low. Thermal fluctuation happens here, And if you do it just one time, it'll probably have a little, random error, high or low. But if you do it 2 times, those random errors could cancel out. Oh, but if you do it 10 times, the more times you do it, it's all if you take a statistics class, which I highly recommend, it'd be very useful for you. But the more measurements you make, the more you can minimize the effect of random error. Systematic error, though, it's like if I'm, throwing knives or something, or shooting archery or throwing axes, especially with archery, maybe you're shooting at a target, but you're always hitting to the left a little bit. And you're like, well, why am I off target? What's going on? Oh, I forgot about the wind's blowing that way, or something's wrong with the way I'm holding it, right? There's something I'm doing wrong where if I had a coach, I hired a coach, I could fix that, right? I'm your coach. I'm your chemistry coach. It's not a sport per se, but I can be in lab. And if you're having a hard time hitting your target, like maybe this is the true value and we know it, and you're running experiments, you can't hit that true value. So you're always low or always high. That's a systematic error. I can watch you do it and go, boom, usually within a minute or two, go, that's your problem right there. Yep, boom, fix that. You're right on target. Yay, get rid of. So that's why we practice. We have practice unknowns to get rid of or, fix any kind of systematic error due to technical issues on the human part of the equation. But all measurements have 3 parts, right? A numerical value, right? My kids, even when they're little, they'd run around with a ruler, 6, 4, whatever. They didn't have concept of units when they were super, 2 or 3 years old, but they all lived around, and that's bigger than that. So they had some concept of a numerical thing. They throw a number at it. But there's more to it in chemistry than just the number, and I'm sure you can all measure the number. Of course, you've got to have a unit. In chemistry, just in anything, if you have a number and there's supposed to be a unit associated, put the unit. If I say, go get the mass of this calculator, and you come back and say, 52.7, I'd be like, that doesn't even mean anything, right? If you don't throw units on it, it's just, a chemist will just laugh. Be like, what? That's a useless piece of information, right? It's like saying, hey, how tall are you, Dr. Locks? Yeah, 241. Okay, awkward silence. You're right. You got to put a unit so that you have clarity in communication. Otherwise, you're forcing someone to make an assumption on what you meant, and that usually doesn't lead to good things. Just check any relationship ever. Don't make assumptions. Be clear in your speech. But I thought you thought that. I knew you knew what I was thinking. No. All right, and then, of course, besides the numerical value in the unit, we have uncertainty, which go watch the absolute uncertainty video, how to determine that, because every measurement, they're not exact by nature. If you have a linear scale or a graduated measuring device, you're in between the lines on it, you got to estimate that. Like I said, if you got even a digital balance, sometimes that last digit fluctuates. There's some inherent uncertainty in the last digit of a measuring device. Right? And so we have to estimate that digit. We want to do it to the best way. So this video is how to do that properly to minimize or eliminate any kind of systematic error possible. We'll look at things like parallax error, reading things upside down, yada, yada. So numerical value, unit, uncertainty. Right? Don't even try to make a measurement unless you know what unit it is and what the absolute uncertainty is. Ha! So let's look at the steps of making a measurement and walk our way through the nitty-gritty details, my friends. All right, here's some steps for you, my friends. Obviously, the first two things you have to do, and 1 and 2 can be out of order, doesn't matter, but determine the absolute uncertainty. How many decimal places can you read it to, or where is the estimated digit or uncertain digit? And again, check out the video for the 3 steps to determine that. And then second, what's the unit? Or you can do the unit first and then the absolute uncertainty. But do those before you even attempt to make the measurement. It's critical. And then step 3, we want to know where we're reading our measurement to. I call that the reference point. Determine the reference point we're making that measurement to. Where is the point? Now, when you're looking at rulers measuring the length of something or thermometers, that's usually not a big issue because you just go, well, it's obviously right there. All right, so we could draw a little line across here and go, that's our reference point. We're going to read to the top there, and we can see where it falls in between those increment lines, right? But when you're dealing with liquids in a glass, burettes, graduated cylinders, measuring pipettes, those sort of things, oh no, you get that curved surface. Well, look at that in one of the later lectures in second semester general chemistry, but if that's water or an aqueous-based solution, it's very attracted to the glass. We'll find out they're both polar if you don't know what those words are. But it pulls the liquid up, right? It's a really interesting topic, but not the topic for right now. But if you see that liquid creeping up or pulling up the sides because it's more attracted to the glass than to itself, that creates a meniscus, a curved surface. Now let's see if I always get concave and convex backwards. Always had trouble with that. Pretty sure that's a concave meniscus. Pulls up like that. Well, now we got a problem. Do you read it here where it touches the glass? Do you read it from the bottom? Do you do the average? You see how you can have some issues if we don't have a common reference point. So in chemistry, if you have a concave meniscus like this that creeps up on the sides and it's a clear or lightly colored liquid where you can easily see that meniscus, we're going to go from the bottom. So let's go from the bottom. Boop. So that's going to be our mental reference point. So we're going to read from the bottom of the meniscus if it's a lightly colored or clear liquid with a concave meniscus. Now, what if you have a liquid with a convex meniscus where it's more attracted to itself than it is to the glass? So you see it pulls up. So you'll see this with like liquid mercury thermometers or a barometer, right? When you see the mercury, that tends to happen quite a bit. So I'll put that in here. So let's say that's liquid mercury or something. Well, it really doesn't matter what the color is of that liquid because we all agree that top is going to be easy to see. So we're going to go from the top of the meniscus. Boop. So there's our reference point. We're all clear. We got to make sure we agree on our reference point. Otherwise, if you read it from the top and I read it from the bottom, we both think we're correct and now we fight about it. Yeah, it's a problem. So convex meniscus, always go from the tippy top. If it's a concave meniscus, always go from the very, very bottom of that meniscus. We're going to need some help to find that, assuming it's a clear, light-colored liquid. And that's pretty much everything we're going to deal in first semester of general chemistry. Second semester of general chemistry, at least in my labs, we're going to be dealing with some very, very dark-colored liquids that are so dark. How dark are they? They're so dark, we can't see the meniscus bottom anymore. So we need a different reference point. So if we've got a concave meniscus, so this is also a concave meniscus. But we can't go from the bottom, so what we're going to do is we're going to go from the edge. Because it's a dark colored liquid. We can't use the bottom of the meniscus anymore. So pick the side where it just touches. You can do it there or there, but I recommend pick left or right. Don't do one on the left and then one on the right. Right? Do them all on the left or all on the right. And if you're reading and trying to compare with someone else, ask them, did you read from the left side or the right side, if you want to be as close as possible. All right, there's more steps. I just ran out of board space, but that's a key one. Find that reference. What's the absolute certainty? What's the unit? Where's the reference point you're going to make your measurement to? Let's look at the next batch of steps. Step number 4. Now we've located, well, specified, we haven't located it yet, specified where our reference point is that we're going to be reading it to. Now, like I said, if you're measuring a length or using a thermometer or something, that's easy. There's no meniscus on it. You're off to the races. So you don't need to worry about step 4 if you don't have a meniscus. But if you do have a curved surface, so let's say we have a lightly colored liquid, and we're going to go from the bottom of the meniscus. This is our reference point. Right? I want to read that reference point. Well, the problem is if you're looking at a clear or lightly colored liquid, so here's just some water in here, it's that meniscus bottom actually has a thickness to it, so it's pretty tricky to find specifically. You want to locate the very, very bottom. So grab a reading card. I've heard them called meniscus reading cards, burette reading cards, whatever it is. But see, it's got that black rectangle there. So what I'm going to do is I'm going to bling. I'm going to bring that black rectangle just underneath that bottom of that meniscus. So when I'm lifting it up, I don't know if we can see it on this video real well. When my hands are jiggling, right? Normally this would be sitting on a counter. But let's say we've got that meniscus bottom. Now watch as I bring this closer and go. See the top of that black line? Watch as it gets closer. You see it outline that in black there? Oh, my hands are jiggly. Or we're having a minor earthquake, one of the two. But you can see how it outlines the bottom of that meniscus in black. You see that? That really allows you to find it. Okay? That very, very bottom of that black part. So I like to get just a tiny, tiny bit of space. Yeah, maybe half a milliliter. Or half a millimeter. Where I'm bringing it up closer, 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 and I just have a little bit of white space in between there. And you can see the bottom of that meniscus outlined in black. So I'm going to get that reading card to where it's just underneath there. So that would be my burette reading card, right? So this is my reading card. And you get that black line just underneath it. And you'll actually see this outline in black. And then you want to go from the very, very bottom of that. Not using this won't create a huge amount of error, but it would create a systematic error. Whoa! So I would get adept at this. So actually, it doesn't matter. Anything that has that black line on there that allows you to do it. And you'll find that sweet spot. It's like looking, if you've ever been to malls with those pictures that just don't look like anything, but you sit there and you see a bunch of people staring at it. There's the unicorn, or there's the Pegasus flying across the castle. You're like, I don't see it. So you got to sit there and you just kind of stare at it for a while. And every once in a while, if you look at it just right, like you're looking through it cross-eyed or something, just that picture just appears. You're like, whoa, where did that come from? I don't know what those are called, but they're pretty cool. It's the same thing. When you're lifting this up, it's just kind of like, you're like, where is it? Where is it? Where is it? Zoom. There it is. I can see the bottom of that meniscus outline in black. Nice. Now, if you're going with a dark liquid to the top, usually I'll use the white side to find where the dark liquid touches to the top on that. All right, let's go to the next step. Once we have notated where our reference point is, and we've used that reading card so we can find the very, very bottom of it if it's a light-colored liquid. This is only if you even have them. If you don't have a meniscus, you don't need to worry about it, right? That's why we like thermometer readings. So let's say we've got a lightly colored or colorless liquid. Did I say clear before? We want colorless liquid. And we are going from the bottom of the meniscus. We get our burette reading card on there. So we've got our reference point. So there's our reference point. We need to avoid parallax error by lining our eye up level with that, right? Because if I have this, right, I need to line my eye up level to it. Because if I'm down low and I'm looking up this way, can you see how my line of sight hits up a little too high? Or if I'm up too high and I'm coming down, you're going to get values that are off a little bit. You got to make sure your eye's lined up. Okay? So here's your eyeball. Probably bloodshot, right? That kind of stuff. So you want to line your eyeball up nice and level with that. Otherwise, if you're up too high, right? If you're up here, you're looking down and you're not on the correct path. If your eye's down here, you can see you got an issue there. So you want to be level with it. Now, obviously, if this is sitting on a counter, you can adjust yourself. In worst case scenarios, you can get your 2 fingers on there. Don't grab it because it'll tilt it, right? But you can loosely hold your fingers and then move this up and down, level with your eyes, right? I can be like, ooh. So I get my Burette reading card, right? I get it behind there like this, and I move this so I'm level with my eyes. Boom. All right. Now, there's also some more advanced tricks you can use with that. If you're trying to figure out where you're at, let me pause this and draw so you can know roughly where your eyes are. One little trick you can do, usually in first semester of general chemistry, just try to line your eye up with it. Ideally, leave it on the counter and then move your head down to match your eyes with it. Do the best you can. That's probably okay at this level. But if you want to get a little more in depth on it, you can use, you'll notice on measuring devices, you've got these increments where the etching goes all the way around or all the way across, or at least halfway, and then these smaller increments don't. This allows you to kind of estimate where your eye is. For example, let's say you have these 2 increments that go across and you're looking at that one. So say, for example, I'm this and I've got the 10, make sure we're going up. We got the 30 and the 40, all right? So let's say I'm staring at the 30 line, right? I'm staring at the 30 line. What happens if you're staring at the 30 line, you can see the 40 line wrap all the way around. You can see the line, the etching in front, and you can see the etching in back, and you see an oval with a width to it, right? You can see that width. If you're staring at the line, the etching coming out in front and the etching behind overlap, so it looks like a flat line. So you know where your eye is leveled to, right? So if I'm staring at this line, that will have an oval to it. But if I switch it, right, and then I go, from this one to that one, and now I'm staring at this one, that oval will shrink as my eye gets closer to it until it becomes a flat line when I'm right on it. Then the front and the back overlap each other. But the further I get from this one, the bigger that oval gets. So now I get a width of an oval there if I'm lined up with that one. And if I'm halfway in between, then the oval width should be the same because I'm not looking at either increment. So I'm in between. So you'll see if you're exactly halfway between those 2 increments, the oval distance width is going to be the same. And let's say you move down. The closer you get to this one, the thinner it becomes and the thicker that becomes until you end up here. Or if you shift up, the thinner this becomes, the thicker that becomes until you end up here. And so you can use those oval widths to estimate where you are in between those 2 lines. A little more advanced than necessary at this point, but it's something you can work with your professor on. It's kind of one where you got to be elbow to elbow so you can, they're right next to you holding it and you can see those oval widths on there. Kind of hard to do on this video here. All right, doable. Let's do the last step. All right, this last step is a little more challenging for first-time lab people. We are going to take that increment, right? So if we're looking in here, so let's say our reference point is in between some of those divisions there. Well, how do you estimate that last digit, right? That uncertain digit. We're going to mentally take that increment and break it up into a certain number of divisions. We're going to mentally slice it up. Chop, 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 chop. Well, how do you know how many mental divisions to make? It's equal to the family. This is where the family comes into play. Family helps us calculate the absolute uncertainty, and it helps us estimate that uncertain digit. So the bigger the family, the more mental divisions you can make. So 10's family, you make 10 mental divisions. 5 family, 5 mental divisions. And the 2's family, just slice that increment in half. Obviously, the bigger the family, the more divisions you have, and the more likely that mental division is going to fall on the reference point that we made for our measurement. So whether that's a thermometer with a point, a meniscus bottom, a meniscus top, depending on the colors of liquids, if it's concave or convex meniscus, you look at where that mental reference point is that we're going to measure, and then we're going to break. So say you've got an increment, and you break that increment into a bunch of mental divisions and pick the one that falls on the reference line that you're trying to read or closest to. Now for the tens family, you're making so many mental divisions, it's going to probably overlap. If this is our reference line, say the bottom of the meniscus, and our mental division will probably overlap. That's why we like the tens family. But with the twos and fives families, if this is our reference point that we're measuring, sometimes it's not there. It's not right on it. There's not enough mental divisions to overlap it. So you pick the one closest to it. Drives you crazy, right? You're like going, it just goes against what your gut is. Word of warning. Don't go mental twice. Very common with the twos and fives families, where you'll take a mental division, break it up into a bunch of, you'll take an increment, break it up into a bunch of mental divisions, and then break those mental divisions into mental divisions. You can't go mental twice. You can only make one set of mental divisions within an increment equal to the family. Let's end this video by practicing 2 or 3 of these to show you how to make these measurements properly. Let's put it all to practice, my friends. Let's say we've got a thermometer. We're measuring the temperature of some liquid or room temperature, the air, whatever. And you can see our line. Let's say we got like a blue alcohol in there, something like that. So given this information, give me the measurement. Now, later on in the semester, we won't do steps 1, 2, and 3. We'll just do it in our head. But give me the increment family, calculate the absolute uncertainty, and tell me what the measurement is. So pause it, give it a shot. I will walk you through it. Let's do it. All right, increment, you can probably eyeball, but let's calculate it. Let's go pick any 2 things. Let's take 30 and 20. So let's take 30 degrees Celsius minus 20 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Take the difference between any 2 values on the measuring device and divide by the number of increments between them. It doesn't matter what 2 values you pick. You get the same answer every time. So 30 minus 20 degrees Celsius is 10 degrees Celsius. That would give us an increment of 1 degree Celsius. Does that make sense? 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Makes sense, right? Now, do you see a 2 in that? Nope, not the 2's family. Do you see a 5 in that? Nope, not the 5's family. That is the 10's family. Like I said, you can probably do those in your head. So we can calculate the absolute uncertainty now, which is the increment divided by the family. Increment's 1 degree Celsius. Divided by the 10 is 0.1 degrees Celsius. If you want to put the plus or minus there, you're welcome to. The first non-zero digit is in the 10th place. So we're going to read to the 10th place. Or to 1 decimal place. Every reading with that particular measurement. So let's get our reference point, which is going to be, we don't have a meniscus here, so this should be pretty straightforward. So our reference point is right there. Right? Line your eyeball up there. My ugly eyeball. I gotta love my Pictionary skills, right? So avoid parallax error. Not as big as an issue for thermometers. It's mainly for graduated cylinders, burettes, measuring volume. So we don't need a reading card or anything like that. This is pretty simple. So that's our reference point. Now what I like to do is identify the 2 increments, one above and one below. I like to see what those are, because otherwise sometimes you might, like a burette is upside down and you lose track of that because they're not written on there. So I like to identify those. So this is 20, 21, 22, 23. So this is 24 and that's 20. So it's going to be 24 point something, right? I'm pretty confident on the 24. Y'all agree? It's going to be 24 points. It's getting bigger going up. Burettes are opposite, right? Burettes start at 0 and go to 50 on the bottom. Be careful about that. Now, let's break this increment into a number of mental divisions equal to the family. The family is the tens family, so I'm going to mentally break this up into 10 mental divisions. So 24.0, 24.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 25. So I'm mentally making these little divisions in there, right? And then what I do is I bring this over and pick the mental division closest to that reference point. So it's not quite halfway, so I could go 24.3 or 24.4. Do you see how I'm not certain? I'm certain about the 24, but the tenths place, I'm not certain about that. I have to estimate that. So I would say 123.4. I would go 24.4 degrees Celsius. And would you agree that the 2 and the 4 are both certain digits? Everybody reading this properly, as long as you're not doing, you don't have any systematic error, you're not reading it upside down, we'd all get 24 point something, everybody. But if we passed it around 25, 30 students in a lab, you might get some saying 24.4, some 24.3, maybe a few saying 24.5. So you just see how there's a fluctuation around that uncertain digit. That's why a lot of people say plus or minus 0.1. So a chemist looks at a value like that, and if you say you measured the temperature to 24.4, I understand there's some uncertainty around that. So really it's between 24.3 to 24.5-ish. Best estimate 24.4. So a chemist always allows for that fluctuation in that uncertain decimal point. You can apply more specific statistics to it and get more fancy, things going on. We're not going to do that at this level. But you would agree that this is an uncertain digit, all right? So all measurements contain all certain digits except for the very last one, which is the uncertain digit, which is where the absolute uncertainty lies. So if I just give you a number, you just look for the last significant digit, that's the uncertain digit. These are all significant. All are significant digits. So this is kind of the birthing of significant digits, or sig figs. All the certain digits and the first uncertain digit are considered significant. We're not certain, still part of the measurement, even though we're not certain about it. So if I just gave you 24.4 degrees Celsius and I say, what's the absolute uncertainty? You just look for the last significant digit. What's in the tenths place? It's good to 0.1. Not too bad. Let's do one more and we'll call it a day. Let's whip through this one pretty fast. I'd expect you to cruise through. Let's say we got a graduated cylinder and we've got a colorless liquid, even though I used blue. So let's say it's a colorless liquid. Let's calculate our increment, right? So let's take the two numbers, 13 minus 12, divided by 1, 2, 3, 4, 5, is 1 divided by 5 is 0.2 milliliters. 12.2, 12.4, 12.6, 12.8, 13. Makes sense? There's a 2 in it, so that's the 2's family. Pretty easy, right? Absolute uncertainty is increment divided by family. Our increment is 0.2 milliliters. Family is 2, so 0.2 milliliters divided by 2 is 0.1 milliliters. So we're good to the tenths place. So it'd be like we could get a 12.5, a 13.0, something like that. Let's find our reference point. If this is a colorless liquid, we're going to go from the bottom of the meniscus. Right? Line our eyeball up there. Avoid parallax error. Use a Biuret reading card. Get that up there like that so we can see the very bottom of that meniscus. That's key. I'm going to label these. So 12.2, 12.4. So this is 12.6 and 12.8 milliliters, right? Now I need to mentally break this into a number of divisions equal to the family. The family is the 2's family, so I'm going to slice this into 2 divisions. So I'm effectively going to slice that in half, right? So 12.6, 12.7, 12.8. Those are my only options. Now my reference point, because it was the 2's family, doesn't fall on either one, but it's closer to the 12.6 than the 12.7. So I'm going to go 12.6 milliliters. Some of you might have gone 12.7, but you see that the 2's families and 5's families, because there's not many mental divisions, sometimes that mental division doesn't fall on the reference point. But we would all get 12 something. So these are certain, and the 6 is uncertain, but that's still 3 significant digits. Boom! Unit! Boom! Uncertainty! Boom! Numerical value. We've got it, baby! We can do measurements!